Let me explain about the situation of the Explorer. RCS 120%. The parameter registration has been completed. RF OHC camera Power 1 projectile safety lock has been lifted, and the automatic sequence has been started. Altitude has reached 32 meters. And we're ready to start the fight. That is all. Thank you.
今回の大きな目的はターゲットマーカーを分離して分離したことを確認すること。
タッチダウンに向けてという意味では一番重要な運用になります。これこの運用が変化を分けるんです。注意深く頑張っていきましょう。よろしくお願いします。
帝国同期から合格がされます。
Good morning. This is the Hayabusa2 touchdown live. We'd like to thank you very much to our audience for being here early. For 2 hours and a half, Hayabusa2 developments will be reported, and the control room situation and the changes there will be communicated to you. I'll be moderating this program. I'm science communicator. My name is Yuko Okayama. And from the project member team, we have 3 of them here, and we'll be reporting, all of us will be reporting to you. A supervisor, Mr. Hosoda, and I'll be reporting from the control room after this as the special reporter. System impact device development person. From the development, from the initial operation and the impact device was my responsibility. My name is Imamura. Ion engine overseas station responsible person, Mr. Tsukizaki. I was using the NASA California antenna to participating in the operation. It was snowing in California, but the procedure has been completed smoothly. During this program, we'll be accepting questions and messages from the audience. Use the hashtag Haya2_QA or hashtag Haya2_TD to send us your messages and questions. Hayabusa2 and the mission positioning and what Hayabusa has been done will be briefly explained after this. Mr. Imamura, please. Please use the slide. This is the touchdown operation and a live program of this at JAXA. We're dealing with not only Hayabusa2, and we've done MMX, solar power cells, Okeanos, and Destiny Caesar Juice. This is what we're contemplating for the future. And this is not just a one-off event. Through a multiple number of projects, we hope to obtain more effective results. And today we will be covering the Hayabusa2 touchdown. The sizes of the Explorer is 1 meter times 1.6 meters times 1.25 meters. And when the solar paddle is developed and opened up, it's 6 meters. The weight is 609 kilograms at launch. It's a little bit smaller than a car. It's smaller than we imagined. We hope Hayabusa will do a good job. And we'll do a point touchdown, and we'll be talking about the accuracy, and we'll be referring to these figures later on. The objectives are such. The Hayabusa landed on the S-type asteroid Itokawa. Hayabusa2 will be landing on C-type asteroid Ryugu, which is carbonaceous, and the sample return is the objective. We will clarify the origins and the evolution of the Earth and the ocean and lives by clarifying the mineral water and organic matter interaction. What has been demonstrated in Hayabusa will be maintained to clarify more information. There are lots of C-type asteroids, so there's more of the S-type asteroids. And because it was easy to get there, we did the S-type asteroid first, but we will we'll check more of the minerals and water and organic matter, and so that's why we decided to aim for the carbonaceous asteroid. Hayabusa2 schedule from launch, it would circulate around the sun, and the launch was 4 years ago, and 4 years and several months ago, and it landed on Ryugu last year, end of June, and presently it's here. And Ryugu will start in November or December. We'll leave Ryugu on the November of December, and all the time it'll be circulating around the sun, accelerating, and it followed this trajectory to land on Ryugu. After it lands on Ryugu, this is the schedule. From July to August, observation is the main mission, and it will descend several times to take images. After September, there'll be a touchdown rehearsal, Minerva 2, 1 separation and operation, and mascot separation operation in October has been successful. And touchdown rehearsal was in October. It went as close as 22.3 meters altitude. On the 23rd of October, we did a third rehearsal, touchdown rehearsal, up to an altitude of 12 meters. And then the solar conjugation was in November and December. The Hayabusa was on the other side of the sun, so we did not operate much. And after that, on the 22nd of February, is now the touchdown. And we plan to reach altitude 0. So you've done many rehearsals, and things have been progressing smoothly up until now. Yes. The rehearsal? We've done much of that. Behind us, we have Mr. Imamura and Mr. Hosoda. That's the studio camera there, the white item there. That's 5 times 11. There are 50 of these boxes, and each of these boxes are related to the special training operation that we have done. It demonstrates the training operations that we have done. The black and red parts show failures, and the orange was where we just about received a passing grade, and it's almost passing. The white and green stickers are successes. So if you look, you see a transition from more failures to more successes. Touchdown is toward the bottom. That's where at the end we were successful. Please point to the box where it was successful. It's not that one, this one. The lower right, the bottom right box. That's where we finally succeeded, and we're where we are today. So you've trained 50 times in the past. So we haven't wasted the 4 years after launch. Could you put the image back on the PC? The touch rehearsal 1 and rehearsal 3 is where we went to altitude of 12 meters. That's October 25th. And the cam head, a camera which is on the bottom side of the Explorer, has been used to take this image. You can see the shadow of the Explorer. The width is 6 meters, as you can see. And we will try to take images this time as well. Timing and so forth, if all goes well, we can expect to receive some kind of image. We look forward to that. That is all. Thank you. And let us talk about Hayabusa2, which is in preparation for the touchdown. Hayabusa2 operation started the day before yesterday, and yesterday it started descent toward Ryugu. Could we get the video? Good morning. This is the before start of descent. That's the briefing.
So I was a supervisor, so I was speaking in front. So the gate means checkpoint. There are several checkpoints that Hayabusa2 is expected to go through, and the first one is gate 1. How many are there? There will be 6 in total, including the one at the point of finishing the operation. So project manager is giving words of encouragement. He's wishing for a perfect touchdown. Now, Please keep your mental status cool and level-headed, and have your heart hot and with passion. So after this, there was some time spent on research. So after 5 hours delay, the descent was started, and this is when go or no-go decision was made. So the person who's speaking is the flight director, Mr. Saeki. On-site person who's responsible for the whole operation at site. Please review the sheet for each subsystem again. So we're at the starting point, finally. So that was the noon yesterday, and then here there was a downward descent from the top side, and there was acceleration made for Hayabusa2 toward Ryugu, and there were smiles seen, so that means that progress is being made steadily. Well, there are a lot of things that have caused this 5-hour delay, but people at the site were encouraged, and they just realized that the space is not that easy to deal with. And that was up until noon yesterday. And then this is just a few minutes ago at the final go, no-go decision point. Out of the 6 checkpoints, this was the third one, and this was the D major, the largest one. And the third checkpoint would enable the project to give go to Hayabusa2. And the project manager said go. And we just leave everything to Hayabusa2 from this point onward. And there's very little that we can do. We just ask the Hayabusa2 and wish Hayabusa2 well. And that was the point of checkpoint 3 that they have passed just minutes ago. And so Hayabusa2 is now descending toward Ryugu, and we're watching that as we broadcast this. And there will be several windows to split the screen, and what's on the middle is in the control room. The system and the project managers are seen, and on the right top corner at the touchdown, what will be the movements of Hayabusa2 is shown in this diagram, and if you reference this to see the progress, and then we are going to broadcasting live. And then right corner in the middle is the CG schematic that has been borrowed from Yanagida-san, and then on the beneath that is the actual elevation, 184 meters. This is the 184 meters from which the Hayabusa2 will directly descend. So at what speed it is moving, several centimeters per second is the velocity currently. And then right bottom corner, you can see us broadcasting and also giving various information as the progress is being made. And please switch over to the camera from the top. And in the control room, there are various types of people working, and who's doing what is what I'm going to explain. Please switch over to the PowerPoint. presentation. And here, from this angle, there are several important persons. First is in the middle. Operations supervisor. Right next to him is a commander. SV stands for supervisor, and CMDR stands for commander. And those are the kind of positions that we take often. And supervisors and commanders are controlling the operation progress. And the commands are given to the commanders from the supervisor, and with the direction from supervisor, the commander actually dispatches the actual commands to the Hayabusa2. And then the project manager behind, and right next to the supervisor is FD, the flight director. And the flight director is the person who's responsible for the whole operation on the site, and he collects all the information and make judgment about what's happening in the Explorer and give necessary instructions. And project manager decides go or no go. And those two persons will not come down to the control room unless there are touchdown operations or mascot deployments. When there are very important operations being made, they will come down to the control room. And then further to the back, AOCS, which may not be so familiar to you. This is an attitude orbit control system, Hayabusa2 guidance, and how to fly. And all this is under their responsibility. And whether the landing that they had envisioned would be successful is what we are watching. If you lose attitude in the space, what is going to happen? That would mean that it is in trouble. There's communication from the ground, and in the very narrow space of 6 meters, you have to make sure that you land safely, and everything is being considered. So you point the antenna to the Earth, and solar panel should be directed to the sun to make sure that there's power supply. And with a good control at the destination of 6 meters, you make sure that Explorer would touch down. So this is the crucial role. And how far away are they from the ground, from the Earth? 300 million kilometers. So it takes 40 minutes even for the light to have a return trip. So thank you. Now I will go down to the control room now to keep you updated about what's happening. So I will just leave this studio and go to the control room. Now, this is the control room that you're seeing at the main screen. Everybody is wearing a Hayabusa2 jacket, and it shows really that people are united. And there's so many people gathered in the control room. Is that quite rare? Well, on an everyday basis in the operation, there are much fewer people. Supervisor, commander, and a attitude system, at least 3 or 4. Those are the kind of people that we see. But there are several tens of people now. Yes, all the people who are responsible, the whole pieces of equipment of Hayabusa2 is now being monitored. And there is another room, aside from this control room, where there are people who are analyzing the operation data.
All of the project members are here watching, and there are people watching the YouTube, which are following the development. So it's getting more exciting. Actually, we're running this 24 hours, 3 shifts, 8 hours each. Each shift is 8 hours. So 3 times the number which you see on the screen are actually working. Thank you. Other than the project members, there are logistics and information-related persons behind the scenes who are playing a supportive role. Yes, many people are supporting this endeavor indeed. And so let's go into the reasons while we're doing the asteroid exploration on the touchdown operation. Mr. Imamura will explain. As to why we're doing the exploration, we'll be asking the scientists to explain the details later. But here, let us just give you briefly some information. Within the solar system, why the Earth is the only planet that is rich in water and lives, and there's a high temperature on other planets, or there may be no atmosphere, for example, on Mercury, where it's close to the solar, it's very hot, and where it's the planet is distant, it's very cold. And the Earth is in the right place and is rich in water and lives. As to why we do the exploration of the asteroid, the interaction of water and minerals and other things will be clarified to elucidate the advent of life on Earth. And as you can see, among the solar system, Earth is the only planet that is abundant in water and lives. And we're looking into why this was the case, why this happened, and the conditions against where this happened, and what we need to do to maintain this. We need to obtain more information as to know what we need to do to maintain the Earth as it is. There are people who think that originally there was no water on the Earth. When the solar system came into being 6.6 billion years ago, there was a small cosmic dust, and then it became a planetoid, and then it became bigger to become a primitive planet. And in this development, near the sun, it was warm, and when it's distant, it's cold. Up to a certain distance, water becomes vapor. It did not become ice, and it became vapor. And the borderline at which water changes into either steam or ice is the snow line, and Earth is within the snow line. So it's often called the snowline planet, but it's within the snow line actually. Yes, that's the case. And initially, when the solar system came into being, it was in an area where water became vapor, and so those planets which are within the snow line are mainly made of rocks and metals and have become planets. And outside, the planets contain a lot of stones and metal and ice. And within the snow line, originally people think that there was no water. So according to reports of other researchers, I was shocked to hear this actually and see this image. The Earth we felt had abundant water because the Earth is often called the blue Earth. But if you show on a volume basis with a sphere, and that is the water. The big sphere is the ocean water, and the little sphere is fresh water, that's river water and so forth. That's the little sphere. The big sphere is the ocean, and that is not just the Earth. Outside of the snow line, there are planets such as there are other moons or satellites. Ganymede, for example, compared to the volume, 46% is water. And so considering this, the Earth on the surface looks like a planet of water, but compared to the volume, it's 0.12% water. So there's very little water that exists on the Earth. That's within the snow line, which had been depleted. But perhaps there was something which brought water in from the outside, and this could be asteroid or comets, which brought in organic matter onto the Earth. That's one theory. And as to whether this is actually true. We're doing an exploration looking for proof through a series of missions. We're looking into the origins of what brought water and organic matter to the Earth, and asteroid Ryugu and Mars satellite or Mars moons exploration plan is in the offing. That's the MMX. And MMX is a Martian Moon Explorer. That's Mars Moon Exploration Project. Yes, that's it. And then asteroid Phaeton and the inter-asteroid cosmic dust. Phaeton is not a word which is familiar to us. There's a twin comet mother entity is Phaeton, and that's Destiny Plus. And then you have the comet, the Churyumov-Gerasimenko. Rosetta went to this comet, and lander Philae has been landed. And there's a lot of information about this comet. Rosetta just went there, but Caesar, this is a NASA project, and JAXA will be cooperating. And we would go and obtain a sample and retain it at low temperature. In what way will JAXA cooperate in the Caesar project? One of the key equipments, capsules, will be provided. Hayabusa capsule technology will be applied to the Caesar project. That's right. IFA is the European Research Institute. Institutes all over the world are exploring asteroids and trying to elucidate more about organic matter. When this is brought back to the Earth, state-of-the-art technology will be used to analyze, and we have the people who are analyzing who will be giving you more information. And that's the strength of bringing back samples. And that's the plan with regard to the asteroid exploration and the reasons we're conducting this exploration. And let me now explain about the touchdown. The touchdown spot, that's the Ryugu C-type asteroid L08. That's within the red square that the landing will take place. So what do you call this? This is a flat development Mercator method. Perhaps this is the Bravo crater. That's where the landing will take place. The middle is the equator. This is the Bravo crater. That's a fancy name. And then you have Kintaro, Urashima, Momotaro. These are names of craters. These are names related to from fairy tales in Japan. Ryugu also comes from a fairy tale, the Urashima Taro story. How did you come to decide on these names? We've solicited names. We've asked people to offer names, and people from all over the world came up with names, and we've shortlisted this. These are the names that have been suggested, and the project members decided. I was not a member then, but yes, the project members, I think, decided. I don't remember very well, but I think we decided, made the final decision over a drink or so. Yes, these are all good names. Water and organic matter exploration, because this is what it is. These are names related to water. Bringing back the sample is like bringing back a magic box, which appears in the fairy tale of Urashima Taro. This is a fairy tale familiar to all in Japan. Before that, the asteroid names were numbers, which were very complicated and hard to remember. Project members all remember the code names 1999JU3.
So, from overseas, there are some names offered based on mythology from overseas, not just from Japan. And this is touchdown operation plan. Around 8:25 in the morning, it is expected to touch down. And with regard to the time, this is what we can confirm at the time that we can confirm at the ground on the Earth. So one-way trip takes 19 minutes. So actually on the Ryugu, 8:06 is the time for touchdown. And 19 minutes after, on the Earth, we can confirm the touchdown. And then radius is 3 meters. Within the circle of 3 meters in radius, the touchdown should be done. And target markers with the flash, there will be a white light coming out from the target marker. And then right next to that, the touchdown will be made. So is it going to be a mirror? No. If you put a light on it, then it will be the light coming back, not like mirror balls, but the whole sphere will return the light. So the radius is 3 meters, and Hayabusa is 6 meters long. So with the same area, you have to park your car, so to speak. Yes, within this space of 3 meters in radius, if the sampler horn can be placed, then that should be okay. But there is only a margin of error of 3 meters. Yes. And project manager has had a very good analogy, so that will be explained later. And this is the touchdown sites L08E1. There are some bumps, but we have chosen the site which has the fewest bumps, ups and downs. And this is next to the target marker, and this is the three-dimensional image. And next, this is also a three-dimensional view. And then the attitude of the Hayabusa2 at the time of touchdown. There is the Earth here, and the Ryugu is described as a sphere, but Hayabusa is positioned in between all the time, and home position is 20 kilometers away. But currently, the altitude is 180 meters. So it's getting closer to Ryugu. And so this is the relative positioning is kept all the time. So Hayabusa is not circling around Ryugu. In other words, Hayabusa2 is not an artificial satellite, but an artificial planet circling around the sun. And Mr. Hosoda just told me that altitude is already 64 meters, down to 64 meters already. And currently, on Explorer, Explorer is now passing right above the target marker, and so telemetry is still visible. The data from the Explorer is what we call telemetry. The signals, in other words. So we have spent too much time on crater names, but so I have to rush. So touchdown operation sequence is shown here. Currently, we are around here, 60 meters. So this, from last night, from home position of 20 kilometers, it has been descending steadily and with 10 centimeters per second in speed, and at the elevation of 45 meters, the mode will be switched and changed, and then it will touch down and then start to rise again. That's the sequence. And after 45 meters, this is more detailed picture. So this has been the image that was shown on the right top corner on the screen all the time, which is quite hard to see. We don't have much time, but let me explain. We are exactly at circle 1, down to 45 meters in altitude with 10 centimeters per second, and it will hover at the altitude, at this altitude, and the LiDAR and LRF, both altimeters will be used. And then antenna will be switched over for high gain to low gain, and the signals will not be received. What do you mean by high gain and low gain? The larger directional antenna, which should be pointed to Earth, but the attitude will be changed. Then the antenna will be switched over to low gain antenna. This antenna can send signals 360 degrees with weaker signals. So you can actually take the central position with this antenna. And with the Doppler effect, the distance from the Earth and the speed are the only one that we can tell. Then, afterwards, target marker will be captured. And as it captures the target marker, it will keep descending, and then parallel movement is performed, and then with a parabolic trajectory, it will go down and then touch down. And signals from the Explorer will not be seen during this time. So the only information we have is from the Doppler. So we are just about to enter into that period. Mr. Hosoda, what's the status of control room? Can you hear me? I guess not. Mr. Hosoda, can you hear us? No, not yet. And there are so many people who are standing in the control room watching the screen. Hosoda speaking. Target marker, whether it has been captured or not, that signal is now coming in, and so everybody is now watching whether the signal has been received. So there is data from telemetry for timeline still there. Mr. Hosoda, can you hear me? Yes. So the data will disappear soon. Yes, we can hear you. Whether the target marker can be seen, the information will come, but Explorer will be tilted for a touchdown shortly, so the signals will disappear. So let's switch over to the video. So Hosoda-san, if something happens, please let us know. Please switch over to the personal computer. So as Mr. Hosoda said, there's a switch over to the attitude for touchdown, and that motion is now being shown in CG. This is at the time of the planning. So touchdown sequence, this red circle portion is the one that it is now being performed. And position is being tilted, and then parallel movement is done. And while watching the target marker, it will be shifted toward that point. And this is the images of ONC camera. The white is the target marker, and this will be the benchmark. And offset is going to be done. And green has a 3-meter radius, and the Explorer is 6 meters long. What do you mean by offset? Well, in the Hayabusa1, it was looking at the target marker in the center, but with this, the target marker is viewed at the edge for landing. So they are going to touch down, or it is going to touch down without address. Mr. Hosoda, what's happening in the control room? Well, the attitude has been changed for the Explorer, so the screen information is gone now. So from now on, we're just going to depend on the speed information, and it seems that things are going smoothly as scheduled. So based on the pre-dispatched command, the Explorer is now moving on its own.
Then let me continue to explain. Back to the PC, please. Initially, we envisaged one touchdown within 100 square meters, and that's now been reduced to 6 meters square. This will be a top pinpoint touchdown using offset, different from the Hayabusa touchdown, which we initially envisaged. This is an analogy by the project manager. Yes, within the target the target marker capture has been confirmed by speed. The target marker has been captured. Hayabusa2 has captured the target marker, and now finally it started to move in preparation for the touchdown. We're getting very excited. And if you could switch to the PC once again, this is where we are. The target marker has been captured. That's number 2. Can you not show where we've clicked it? That's number 2. And target marker has been captured. The TM has been captured. It has descended considerably. It will descend considerably up to 8.5 meters. From altitude of 20 meters, it will go down to 6.5 meters. That is the analogy. From altitude of 20 kilometers, it's like going down to the Koshien baseball ground. It was 100 meters times 100 meters, but it's like landing on a mound on a baseball field. That's the analogy. Even gliders cannot achieve that kind of accuracy, and so using the Hayabusa method, the target marker would be in the middle, but we've offset the target marker, and by so doing, the pinpoint touchdown will take place, and that's the method we have opted for. The touchdown operation plan and the philosophy behind it, we give priority to safety. The Explorer is moving automatically, and if something goes awry, it will abort. And when abort takes place, the safety of the Explorer will be secured, and so we could retry. And the abort designing has been very rigorous to ensure safety of the Explorer. That is all. Thank you. And from here on, we will go more into depth into the science. Mr. Fujimoto and Mr. Watanabe and Mr. Tachibana and Patrick, project members, will turn to you to go into depth about the scientific aspects in detail. So over to you, please. Good morning. I'm Vice Director of JAXA. My name is Fujimoto. The four of us will be explaining what happens after the sample has been extracted, and international cooperation is another matter we'd like to discuss. We're very excited, and today's event is very much under focus by people at JAXA, and the message from NASA is what we'd like to show you first.
Acting Director of the Planetary Science Division at NASA headquarters. On behalf of all of NASA, I want to wish the Hayabusa2 team good luck in the attempt to touch down on Ryugu to retrieve a sample of its regolith. With every one of the spacecraft's achievements, with every piece of data collected and every image beamed down to Earth, and now with the collection of a regolith sample, The Hayabusa2 team is bringing us closer to answering fundamental questions about the origins of the solar system, about who we are and where we came from. Thank you for all your hard work and good luck.
So, Lori, good luck to you. Good luck to OSIRIS-REx. When we have both samples from both missions, that's going to maximize the science output for planetary science. So, NASA もです。
OSIRIS-REx is a similar mission to Hayabusa. So they're making maximum efforts, I'm sure, to ensure success. And that we get samples is very important for our community. Mr. Watanabe, for 8 years, you have been a project scientist, leading the scientists. What is your take on what happened this moment? At the JAXA, we have a lot of very competent researchers, engineering members have been very active. And in addition to this, on the domestic scene and overseas, we have had cooperation from the experts. And we have a very good collaboration, as a result of which we can look forward to operational success, and we've obtained results, and we've worked very hard, and some had work related to the universities. In addition to this, we've done this, and we're very happy that as a result of this, we're witnessing this wonderful event. There was some news earlier that about the target marker. 180,000 people have their names on the target marker, and so the target marker is supported by various persons. That's very symbolic. What is your view on this? 180,000 people are involved, and so I hope that the touchdown will be a success in view of this effort. With regard to sample return, I think it 4.5 billion years to extract the sample. Organic matter, water, which has come to the Earth through an asteroid, was the origin of life. And as a result, human beings evolved, and these human beings are now going to Ryugu with a target marker to return a sample. So this is a 4.5 billion year sample return, and after 2020, we'll have a sample return. So there's this dual aspect. The present planet science and the direction which is headed to has been just referred to. Before the Explorer lands, the Minerva robot landed, and using the data obtained, sampling final tests have been done, and we're just about to do the sampling. The final preparation was one in which the leader was involved. So could we have you explain, Mr. Tachibana? Yes. Could you show the video, please? The sampler team, ever since the launch of Hayabusa2, has had the same projectile as the one that is on the Explorer, and we've done experiments. The Ryugu surface situation, thanks to Minerva, is such that we know the details. So we've reproduced the same surface, and we've done tests as to what happens. And if you could look at this video. The projectile has been fired, and that has been confirmed. Once that is confirmed, the surface particle behavior was seen. As you can see, a large crater is created, 10 centimeters, and lots of particles are expected to come out. Several centimeter rocks will be fragmented. The smaller ones are easier to extract, and we've observed Ryugu, and we've seen the surface through Minerva, and that's why we could do this experiment. the typical sample size was questioned on the web. Could you have an answer to this? Under 1 centimeters, that's the maximum size. With this size, there's a lot of information, and we can extract a lot more information. 1 centimeter is a sufficient size. Is that what you're saying? Yes. From France, we have a planet scientist, Patrick Michel. So I'd like to ask the following.
What made you crazy about Hayabusa2?
Oh, well, first, it's very exciting to be here. I'm crazy about Hayabusa2 because it's a very ambitious mission, like Japanese like to do. And it has many firsts. So it's it made the first detailed image of a potentially carbon-rich asteroid. It made the first deployment of mini rovers and a French-German lander on the surface of such a small body. And it's going to be the first sampling on an asteroid. So this is the first reason why I like it.
Hi, Patrick.
Patrick Michel has been a great supporter of Hayabusa2, and I asked him why he likes Hayabusa2, and he said that it's a very ambitious mission and it's the world's first. It's first in many respects. Resource type of asteroid is very attractive, and a detailed exploration can be made, and observation can be made, and small robots can be deployed, and as we're doing now, sampling can be done. And so lots of firsts, and it's a very ambitious mission, and he's a fan of the project because of this.
Is that all these operations are extremely complex, and yet they were extremely successful so far. And I could observe the dedication and the courage and the effort of this team, which was able to even revise the strategy for landing because we had to adapt to a new situation. We did not expect so many rocks. And to see how they were able to completely change the strategy and lead to this moment we're living now, it's fantastic.
And furthermore, he said that once the mission was started, when you get there, the situation that you saw on the asteroid was totally different than expected. But timely strategy change was done, and we are now at this We have now arrived at this time, and it is quite exciting.
Collaborating in Hayabusa2. This is not the end of our collaboration story. We have MMX as the next step. So maybe you can tell us about MMX.
Yeah, so
and European contribution to the MMX.
Absolutely. So that's actually the third reason why I like Hayabusa2, and of course MMX, is that it shows that science has no frontier, because we work, we are scientists from around the world. You invite us on your mission. It's very great, and it shows that despite all the geopolitical tensions in the world, when we work for knowledge, we erase all frontiers. So that's the first message I want to say.
Hi, Hayabusa2 then.
So in Hayabusa2, the Japan-European collaboration is quite exciting. There are a lot of things happening in international politics, but the scientists and engineers can collaborate, and he is happy that he is part of that
the Martian
collaboration.
moon Phobos, and it shows something which I really appreciate in Japan, is that you have a vision. You have a roadmap, you know what you want to do. You started with a sample return from Itokawa, which was an object formed at closer distance from the sun. Then you go to Ryugu, which is a little more primitive. And now you're going to go to different boundaries. So understanding the Mars environment, and maybe later go even at further distance. And I think this is really a great thing, because it shows that you have a plan which is well thought from the start, going from smaller distance from the sun to larger distances from the sun, with sample returns and in situ observations. And I think this is very fundamental in science, to have a long-term strategy. And I'm happy to see that Japan is able to do so, and to involve us in these adventures.
And also, as regards to small body asteroid exploration, it is easy to collaborate with Japan, Itokawa, Hayabusa2, and MMX, because you're starting from the asteroid closer to the sun, and then go to the more distant one in order to solve the issues. And Japan has a long-term vision, which is quite impressive, and European scientists have been invited, and that is something that he appreciates.
Brian May is one of your best friends, and I think we have a video clip from Brian. Is that correct? So,
yeah, he kindly made this video for us before going to the Oscars.
Hi, Brian May-san.
So from Brian May, we had a message sent to us, so please take a look.
Konnichiwa. This is Brian May, and I'm very honored to be speaking to you beautiful people of Hayabusa2 on this very auspicious occasion. I have a long history with Japan, as many of you will know, and Queen, my group, has had a long love affair with the Japanese people. From the days when we first came and Queen was a hit with the young people in Japan, right up to the present day when our Bohemian Rhapsody film has absolutely triggered a cultural phenomenon, and we are so happy and so honored that we have this contact. But I have also been following Japanese astronomy and Japanese astro endeavors. I was looking at Hayabusa2, the mission to Itokawa, from a distance, and happy to find some images which I could make into stereos. Now I'm hugely happy to be, in a sense, part of the Hayabusa family, because I've been able to process some images from Ryugu. And this has been a thrill, and it's a labor of love for me to be able to contribute something. So I'm here to wish you absolutely the best of luck in this incredibly delicate maneuver to touch down on Ryugu. I can't wait to see it happen. I know it will be a wonderful success. My heart is with you, and give us more 3D and give us more astro adventure. We love you, Hayabusa2.
So, Dr. Watanabe, what did you think? It was a wonderful message. Thank you very much. However, I am an astrophysicist, so I hope he is an astrophysicist. So rather than being a member of Queen, he should come join us. And music and science are close to each other, opening up new fields and come up with something that will give excitement to people. And that is how I felt when I listened to his message. So if there is time, you were supposed to sing karaoke, but not enough time. So as the scientist, project science Watanabe said, in this touchdown image, I hope that he will come up with stereo images. What sort of holes were drilled and what sort of status was done. If he can come up with that, that would be appreciated. And also, if he can compose a song, really good touchdown, that would be.
Well, Brian is really amazing because, of course, we all know he's a talent as a musician. But he also has a very high talent in stereo images. So you send him 2 images separated by some angles, and he transforms them in a 3D image in a very fabulous way. And we joke often because each time I tell him I fall from my chair when I see these images. And he does it like an artist, of course, and he's extremely generous. You can feel that what he wants is to help as much as he can. It's not, for him to be on the front. He's really an extremely generous and accessible guy. It's really absolutely fun to work with him.
So Brian May is, of course, a famous musician. Everybody knows him, but he's an astro-scientist. May I go on? So as an astrophysicist, he is also talented, and he's good at stereo images. You can come up with 3D images looked from a different view, perspective. Soya-san, can you hear us? So in the control room, there was a big applause. So the sequence is progressing at the fastest speed, and we have confirmed the program for touchdown. And whether this was actual touchdown is being now checked. So we did it. Right. We made it.
Well, you know,
job, right?
Queen makes the show on Earth.
Yeah.
Hayabusa2 made the show 300 million kilometers away. The show must go on. It's great.
Yes.
Congratulations. Congratulations.
Brian images.
Yeah.
Okay, so now I can ask you the.
So the samples are being captured, and what are we going to do with those samples? I'm sure everybody is interested. So, Mr. Tachibana, can you tell us your thoughts? So Ryugu, as Ryugu, the name Ryugu indicates, it is related to the ocean, in our view. So we are living on the face of the Earth with the ocean, but we don't know where the ocean has come from. That is a big issue for science. And one possibility is the asteroids such as Ryugu. So once the samples have returned, then we will look at the minerals that have water or organic matters. So where the component building blocks for the ocean will come from. That is what we are going to look at as a new step for the science. And it is not affected by heat, so you can actually date back to the history of solar system, and you can, by dating back to the origin of the solar system, you can also analyze the samples together with the people from around the world.
Congratulations.
Thank you. So just saying that delta V is a nominal volume. So that means that it is exactly right. And everything is going as scheduled. It has been perfect so far.
Success never ends.
And
Patrick says that Hayabusa2 has seen success after success. And any last words from you, Mr. Watanabe? Now that this has happened, do you have anything to say? I'm really moved. I'm very excited. My mind is not where it should be. If the sample is brought back properly, we want to share the results of this with those on Earth. Thank you very much.
Me, Patrick?
Yes, you're my best friend. Thank you. Hi.
Back to the studio. While we were explaining the scientific aspects, we went back to the control room because of the news. So we have a major guest here with us, and so let us reflect back on what happened. Hayabusa project manager, Mr. Junichiro Kawaguchi. Good morning. In the control room, there was a very excited atmosphere, which we've just witnessed. Could we have your impressions? the results is exactly as we planned. There was some deviation from the simulation graph, but the results are such that everything went according to plan, and that's impressive. And so it was the case the previously, but we had lots of people in the control room. People who were involved all came into the control room. Again, this time there were lots of people, and I'm very glad that everyone is happy. In the morning briefing, this is a revenge for what happened 13 years ago, or maybe 10 years, or 13 years, yes, indeed, 13 years. Revenge. The touchdown. Rather than the touchdown, it's more about the sampling. The sampling could not be done according to the designated method. With regard to Hayabusa, there were two things that we could not do. Landing Minerva was one thing. Minerva 2 landed previously. Mascot landed. So that was a repêchage or revenge. So that was a payback. And the sample, initially, in the previous time, we thought that we could collect the sample, but we thought we had collected, but maybe it was an act of God. The communication was interrupted, and we read that the sample was not collected. So the two things which we could not with the Hayabusa. Of course, this time we don't know if the sample has been collected. We have to wait and see. But probably the projectile will be discussed later on. And if the sample has been collected, what Hayabusa could not achieve, thanks to all, what we had tried to do, what we had wanted to do for the 13 years had finally been achieved. The present situation, if we were to sum it up, data from the Explorer has not been arrived at. Yes, the telemetry has to be revived. Everything is going smoothly, but it's important to see the state of the Explorer. We want to focus on this. We will know at 9 o'clock, maybe at over 20 minutes when telemetry is revived. The status of the Explorer is what we want to know. And we're waiting to see with excitement as to the status of the Explorer. During this program, we'll be able to witness that moment. The Explorer has worked according to plan, and we've confirmed that so far. After this, accurate data from the Explorer should be sent back, and we need to confirm that to make the decision as to whether it is okay or not. The gate check was performed earlier. The checkpoint, that's fifth checkpoint, has to be cleared. And if everything is successful, then we can conclude that the movement is according to what we planned. The final decision will be made by the project manager as to whether this is the case. The radio waves are still coming. It's all live. Those responsible are very simple people. When you see the operation of Explorer, you can see that in the morning. First, when they come to the building, they want to confirm whether radio waves are being emitted properly. And that's the important point. And so they're focusing just on that. The important thing now is that the radio waves are being emitted. And that makes them very happy. It's part of their lives, as washing your face in the morning. It breaks if it collides, so that the radio waves are being emitted, everything is going smoothly, and that's 30 billion kilometers or 300 million kilometers away. So it's hard to imagine. You've been leading the Hayabusa project, and it's not just the denominator in astrology that has been broadened, but you've increased the supporters of asteroid exploration, space fans, astrology fans, the children and young people. It's important to feel the excitement of people on the ground. Science and technology advances on the ground, and we hope that this is brought home to everyone. If people experience this, I think it's good. From the control room, Mr. Hosoda is back, so could we have a word from you? Hosoda speaking. Just according to schedule, the touchdown has progressed very smoothly, and earlier the touchdown has been made and the separation has been completed. All of the people, including the system people, were working in solidarity. And so those people who were involved were very tense. But then we saw nice smiles, and they were hugging each other, and I was really moved. And after this, at 5 minutes past, the Explorer will face the Earth. At 5 minutes, the Explorer will face the Earth, and we should be getting information back. And when this happens, we'd like to communicate to you about the detailed information. It was good. Mr. Kawaguchi, when you came here, you had a big smile, and thank you for bringing this atmosphere to the studio. Yes, I'm very grateful. 14 years ago, data analysis, which followed, well, we don't have to do the analysis. It was very tragic. After ascent, the posture attitude was very unstable. The reason for this was when we analyzed, we found that the fuel gas leakage, there was fuel gas leakage. And we had deferred the press conference, and what we were doing in the meantime, we're trying to stop the leakage. And we finally stopped the leakage. And we were at the press conference, but there were no smiles. We were at a loss as to what to do. So we're very happy, and that's good. And we hope that we stay happy. The Hayabusa project, from launch to return, or before launch preparation, and after return, there has to be analysis. One project requires over 10 years.
Yes, that is right. And successor to Hayabusa is now touching down, and this is also a 10-year-long project. How you can develop young researchers, and that is very important. Yes. Well, 5 years in duration would be the most welcome to us, because graduate school students will stay in the university for 5 years, and then they can be exposed to the front line of the space exploration. If that is experience that they can have, then that would be very helpful. But if that is disrupted and there is intermission, then that is not good. So we hope that this will be continued. So with Hayabusa2 success, there must be more people who are coming into this field. Yes, I hope young people will come in and work with the young active members now. So according to the rule, I will be retiring by March this year, but we're not told not to receive the pension benefits so early, so I will stay for another 2 years. So perhaps you can stay here until the Explorer will return. So yes, I will stay here until 2021 to make sure that there will be a successful return. So it is just a one-way trip that is over. So I hope you can focus on impactor. What does this impactor mean? It is to create the artificial creators by having these bullets. And Hayabusa2 has a higher degree of completion, but what should excite people is that this is the first in the world. This has been incorporated into Hayabusa2, and this was the first time in the world. And this is exactly what you mean by opening up the new field, and this must be quite exciting because you're engaged in something that has never been done before. So this is the beauty of being a part of the part of this team. Well, and that is going to be done around April according to current plan, so you cannot keep your eyes off. Now, let us take a look at the messages from via Twitter. So let me share some of them with you. Jill Zusa said that this is the project that has been going on from the first Hayabusa 1, and I'm pleased that Dr. Kawaguchi will stay with us for another 2 years. So that was the message coming in. And the Hayabusa 2 touchdown success, very pleased. So it will return at the end of next year. So I hope it will keep up the good work. Well, Dr. Kawaguchi seems to be extremely happy. And so this is another fan of Dr. Kawaguchi. I thought it would be 8:25, and I was preoccupied by the house work, and I missed the touchdown point. Oh, you can replay the video. So the message to the children who are would-be researchers, and that was the request from Tanaka-san. So when you say space development, you may associate that with the numerical data or signal data. But what's different about Hayabusa 1 and Hayabusa 2 is that you're bringing some materials back. So it's not just about numbers. And this is a huge experiment, or field work, I should say. And so it also comes along with the experiment, and that is the most important point. Hosoda-san, can you hear me? Can you hear us? Do you have anything to say? Telemetry is supposed to come back, so everybody is now getting prepared. So in front of the control room, everybody is standing, nobody is sitting. And everybody is now approaching toward the front side of the room. Well, you have to check the soundness, integrity, and also whether it has fired the projectiles or the bullets, what we call bullets. It takes more time. So Doppler is a display that will show the radio frequency. And that is the only thing that they can watch. And telemetry has come back, and you can confirm that on the screen. Yes, we are seeing telemetry. In front of us, there is one screen that can show the telemetry data. So a big applause again. So everybody is filled with smiles. The project manager, Tsuda, is all smiles. So telemetry has returned. Can you elaborate more on that? So from Hayabusa, there is data coming in. You have to have a big antenna facing the Earth for the data to return. And in order for the spacecraft to touch down on the asteroid, the antenna has been shifted slightly. And now that touchdown is over, the antenna or the explorer is now facing the Earth and now starts to send the data. And that data is now coming down, and more detailed data about the spacecraft is now coming in. The person who's responsible will start checking. Another applause. From the control room, yes, over to you. The projectile firing was confirmed. So in Hayabusa 1, it was not fired. The projectile was fired. So Dr. Kawaguchi, how do you feel? Well, I just want to jump. So this is the most crucial point, whether you can confirm that the projectile has been fired. The project manager, Tsuda from JAXA, and project manager Oshima from NEC are now clapping their hands. And in front of them, the person whose hand is on the chair is the young researcher. And from the manufacturer perspective, he has been controlling the procedure of the operation, and now all his efforts have been now rewarded. So Hayabusa2 will ascend to the home position. Yes. So Mr. Hosoda is now back at the studio. Welcome back. So how did you feel when you were in control room? Well, the excitement of the site was felt, and the people with each of the responsibilities has to be checked and confirmed that their areas of responsibility has been successful, and that has been confirmed one by one. And then the integrity of the spacecraft is now being checked, which is checkpoint 5. So there's only one left for checkpoints. Right. And looking at the answer, the final decision or judgment will be made. So you were not here when there was a most crucial moment that was happening. You missed that. Well, you're supposed to be here much earlier, but you stayed on in the control room and you were late. Right. So thank you very much. And Dr. Kawaguchi has been watching, and that has been quite assuring for the people in the control room. Well, it was the most pleasing experience for me as well. Thank you.
Could you tell us about how you were involved in this project and introduce yourself? As has been introduced, Hayabusa2 posture attitude control is my area of responsibility, and that is how I was involved in the project. From the development phase, I was involved. And after the finish of the development phase, as is the case today, I'm involved in the operation. The attitude control is the linchpin, it was mentioned earlier, and things have progressed very smoothly. Yes, when we moved into the mission phase, a lot of the aspects has proceeded according to plan. And as you mentioned, attitude control system is a subsystem which impacts various other aspects. It's really a linchpin subsystem. And as one member of the team, that this is going smoothly makes me feel proud. Specifically, with regard to Hayabusa2 attitude control, what aspects were difficult, and what aspects did you struggle with? In the development phase, I was involved since the development phase, and toward the launch, there were lots of difficult periods, and even after operation, when it was cruising, things were smooth. But at the mission phase, after landing on the asteroid, there were lots of critical things that happened, and so operational design is something that proceeded before arrival. And the screen is divided into 4 compartments. The young 2 members are the attitude control related. On the left-hand side is Mr. Ono, and on the right-hand side is Mr. Yoshikawa. And next to me is Mr. Mimasu, in their latter 20s to in their early 30s, who are very active on the ground. And it's only Mr. Mimasu that was involved from the development stage. Mimasu and I were involved in Hayabusa 1. We were, as students, involved in the operational aspect when Hayabusa 1 returned to Earth. And he is a senior to me, so I learned a great deal from him. During the development phase, as a senior member, he has given me much guidance. So in this way, knowledge is succeeded. Do you have more men? In the control room, there seem to be a lot of men. And from what I heard, the return control, when we looked at that room, it was just men. Yes, there are some women. There's one woman, but in the engineering faculty of universities, it tends to be more men. And for the same reason, basically, the present status is such that we have more men. What made you involve yourself in the attitude control? Yes, I like space very much. And satellites and spacecraft movement in space is my area of interest. And I thought that in an area where I could play to this motivation was attitude control, was one of the options for me. So it's 300 million kilometers away. And the diameter is several meters, a mere several meters for the spacecraft. And to control a spacecraft is hard to imagine. It's difficult to imagine. It's very far away. And so people have the image that it's hard work and it's difficult because it's far away and remote. The most difficult aspect is that because of this distance, there's a lag in terms of communication with the Explorer. And so people were struggling to find out at which point they could rejoice. One way it takes 20 minutes. So when we wait for signals from the signal, there's a 40-minute delay. So within this context, we have to control this spacecraft. So we have to predict 40 minutes hence to control. So in the area of control, that's the most difficult aspect, the time lag. And this time, in addition, the moment of touchdown or toward the touchdown, communication was interrupted. Yes, the last phase is such that because it's a low reception antenna, and the sequence occurred when we switched to the low functioning antenna, and information was very limited. In the end, Doppler information, Explorer speed information was used, and that was the only thing we could monitor to confirm whether things were going smoothly. So the Doppler is what you were watching to confirm. Yes, if things were going well, the Doppler movement would be so and so, and we had predicted that. And so we confirmed whether what we had predicted was happening. The Doppler is the lag in communication frequency. What is moving brings about a delay in frequency, and from this delay, the movement of the Explorer can be imagined. So the movement has been exactly as verified by the simulator. Can you also predict in which way it is moving? It's restricted to the direction of the Earth. So it's one directional. It's one particular direction only. We're limited to that. the vertical direction movements cannot be ascertained. The Explorer just doesn't move just toward in the direction of the Earth. So it's only one aspect of the movement of the spacecraft that we can confirm. The attitude control has gone very well up to now, but you envisaged a lot of things. So you had plan Bs for different aspects when things did not work out. Yes, it's the calculation and various things. To the extent that we can imagine, we've thought of different things that could happen. With regard to all of the things that we could imagine, we had made preparations and we had made plans to the extent possible. On Hayabusa2, how many on the team were involved in attitude control? With regard to attitude control, the overall head count is about 20, more than 20 or so. In one shift, 6 people would be working. And there are 4 to 5 shifts, so it's 20 people or so. So we've had some questions through Twitter related to attitude control. Imamura-san, could you talk about it, please? From the Shironagasu Kujira, do you use thrusters for attitude control? The science thruster and reaction wheel, do you use both? Could you explain both? The question was about the use of the reaction wheel or the thruster. It's only a lot of professionals are listening. The reaction wheel is a disc that has a certain output, and this rotates. It's a counter reaction which moves this, and it's the counter reaction. The Explorer works in the opposite direction. It's the actuator. Yes, so you have to make sure it doesn't move in the opposite direction. Well, it's the reaction wheel moves in a certain direction. The Explorer moves in the other direction, and we use that to control. The reaction wheel is used for very precise control, and the science thruster, what's that? It's the science propelling system. A rocket engine. It's a small-size rocket engine, you can say. A rocket engine has enormous force, but it's reduced to about 20 newtons or so. What's 20 newtons? So is that difficult too? 1 kilogram is 10 newtons. So 2 kilogram, the push is about 2 kilograms strong. It's pushing with a force of 2 kilograms. Can a human being push it at that magnitude? Yes, it's the size of the kind that human beings will be able to push. It's like a rocket. You use the principle of a rocket, and it's a propellant system, a more forceful system. And the other is used for more detailed control. When you use broad brush propellant, you use the science thruster. But you use fuel, so you want to save the fuel. And you want to control attitude, saving fuel. Is that an important thing to do? Yes, indeed. When it's normal, then reaction wheel is used to stabilize the attitude to descend and to operate. The last phase was such that the Explorer wanted to land on the asteroid, and immediately the attitude has to be changed, and you need the scientific thruster to do the forceful control.
So to get back to what we were discussing, since we are looking at the control room, how many female researchers are there? It's very difficult to count. Right in the middle of the screen on the right, 1/3 from the right. Can you show that? On the screen, there is a commander who is entering the commands, and that is a female engineer. So in the touchdown operation, the person who's sending the command is a female, and she is not a scientist or engineer in the background, but she's a young person, and she has obtained the qualification for radio communication in order to get involved. I'm not sure if to what extent I can go into her private information, but she talks about her pet rabbit during the operation, and this really gives us a relief. And as a Hayabusa2 system operator, there is one woman called Hirose, and also sample analysis is being done by a female called Sakamoto, who is going to come to the studio as a guest later. And HDA and LGA are used for touchdown operation, high gain and low gain antenna. But why is it that you don't use middle gain antenna? Would that affect the attitude control? A question from Mr. Yamamoto. Very core question, hardcore question. In the mission phase, antenna that we use is high gain antenna to return the large volume of data to the Earth. But in today's touchdown operation, there's a very large degree of deviation from the direction of the Earth. Then low gain antenna with a large directionality should be used no matter how much distance away you're from the direction of the Earth. You can send the data, but the volume of data that can be sent is limited, so you want to use high gain antenna as much as possible. And in the middle gain antenna, you can actually move the antenna to point to a certain direction. It doesn't affect the attitude control in the first place, but in accordance with the attitude of the spacecraft, you have to direct the middle gain antenna to the face to face the Earth, and that is very cumbersome. And we cannot tell in what direction that spacecraft will be facing in the end on the face of the asteroid. So that's very difficult. And so ultimately we decided to use low gain antenna to do communication. But middle gain antenna is also incorporated on the spacecraft, so then it is possible that they can be used going forward, yes. So in the cruise phase, yes, middle gain antenna used to be used because it takes a stable attitude, and you know where the spacecraft is facing, and then you can tell which way the antenna should be directed, and that's why we use middle gain antenna, and we don't use high gain antenna for that purpose, because you may not be able to make the antenna face the Earth, and z-axis direction should be facing the sun. So spacecraft is controlled with X, Y, Z axis, yes. And I am a project member, and actually I'm ashamed that when you talk about attitude control, I thought that I understood this. But actually, attitude control is really a complex calculation. But ion engine, you just fire up the plasma, and the plasma should blow the jet and to reach the Ryugu. And that was what they're doing. But right next to us, there is meticulous calculation ongoing for attitude control, and you have to stop that. And that's what we're told. And then you reach the asteroid. So the collaboration is the key, yes. So ion engine is designed to save fuel, or is it important to save fuel? Well, you talked about chemical thruster, but in the usual spacecraft or satellite, the chemical thruster is the only one that you use. However, compared to that chemical thruster, the fuel efficiency is 10 times better for the ion engine. Hayabusa2 has a mass of 600 kilograms, and even if you have the chemical thruster on the payload, it is barely covering the return trip. But with the chemical thruster, you can actually go to the asteroid and then go back with this fuel. So it's very good in fuel efficiency. Is there any disadvantage? With the chemical thruster, you talked about 20 newtons or 2 kilograms. So if the force of dropping the plastic bottle of water or 2 liters, but ion engine is a gradual force that is being generated. So how you can distinguish the use of those different systems to put the spacecraft on the orbit to reach the Ryugu? That is important. Well, in Hayabusa 1, I was not involved in operation at all, but we struggled with the launch of ion engine, and there was very little time for them to prepare for landing on asteroid. But actually, Hayabusa 2, everything was going well, and as long as ion engine is functioning well, then this white, if you can go back to the studio, this whiteboard that shows 50 times of rehearsals or practices, the members of the team were able to spend this much time for training, and that was what the project manager told us, and I really remember that well. And there's a quick question. So MGA will not affect the attitude control, but what about the counter action? Would you rotate the oil wheel to operate? Well, to be more exact, the middle gain antenna, the counter action of the action of middle gain antenna could affect the attitude control slightly, but for attitude control, we use a reaction wheel to make sure that it will be kept in the same direction, and that is autonomous control. So even with the torque from counteraction from middle gain antenna, there is a control force from attitude control system to counter that. So there is very little impact on the attitude control system. So this is not a question addressed to Mimasu-san, but there's a question from a child. So let me read this out. When the capsule is delivered to the Earth, is it going to be delivered to a different asteroid, and then the samples that have been collected, what would happen to those samples? So is there any plan for the samples? And that should be answered at the press conference. As a project member, one project member, if that sort of dream is there, then that would be exciting. I personally think that we want to go to a different asteroid. Well, it's not a sample return mission, but in the US there's an explorer sent out with the ion engine, and after looking at the asteroid is going to the Mercury. But we just succeeded in first touchdown, so we're not there yet to consider that much further down the road. Well, children are saying that this is a dream. Well, not that far away. But in April, May, June, there will be more crucial GCI operations and others will come out, as Dr. Kawaguchi said. So unless we pass through all these operations, we cannot talk about the stream type operation.
Mima-san is wanting to go back to the control room. So could you bring Mr. Sakamoto in your place, please? Yes, I'll do that. Thank you. Earlier in the broadcast, projectile firing, it was said, was confirmed. There was something mentioned to that effect. More accurately, the projectile firing command issuance has been confirmed. You might think it amounts to about the same thing, but the command issuance has been confirmed. That is a more accurate expression. So let me pass this message on. Thank you. At the news, at the press conference, I think details will be addressed starting 11 o'clock, I believe. Hosoda-san is back. The control room is has calmed down a bit. Yes, the telemetry has come back, and people are very carefully looking and confirming, and so we want to keep an eye on this. People have calmed down a great deal, and there are fewer people in the control room. The project manager is still standing, but the others are all seated, and they're all looking at data. In the control room, are there models of Hayabusa2? Any other objects? What's the object, the green object in front of the project manager? That's a Daruma doll. When they went to the shrine at the beginning of the year, they brought this back. And when the wish is granted, the two eyeballs are painted in. And so that is what we want to do. Behind there are photographs of asteroid Ryugu. And what are those photographs of Ryugu? Landing on Ryugu, and Ryugu rotating is being shown here. If you cross your eyes, it looks like it's just one Ryugu. Was it used to determine the landing spot? Brian May took this image, and he created a green and a red colored image. If you would use a special glass, it looks like a 3D object. He's very talented, isn't he? Yes, he's a scientist, astronomist. We have two people here now. Mr. Sakamoto and Mr. Tachibana. Mr. Tachibana talked to us earlier. Sakamoto-san is responsible for curation. So what does the curation person do? Could you introduce yourself? Kanako Sakamoto is my name. The samplers, the containers containing the samples, and the container, when it's brought back, we would open it. Yes, and we have to carefully manage it so that earth substances do not enter the container after unsealing. And we distribute it to the researchers, and we're making preparations for this. and I'm responsible for that. The post-sample return work is what you're responsible for. Yes, in terms of curation, we're waiting for the sample return. The researchers all over the world want to get their hands on the sample. Yes, I hope and pray that we could actually bring back the sample. Could you introduce yourself once again, Mr. Tachibana? Sampler and sample analysis and putting together all the results is my responsibility. The analysis, specifically, how does it proceed? I'm sure researchers worldwide want the sample. What are the rules? And what is the sequence? Could you briefly explain? First, as Ms. Sakamoto explained, the curation in the facility which will be created, we confirm once again whether what has been returned is from Ryugu and what is the volume and what is the size. Before coming into contact with air, we make decisions on these points. And after this is done, a part of the sample we send to analysis within Hayabusa2 team. And as mentioned earlier, as the name indicates, the origin of the ocean and the origin of the solar system will be studied, and scientific analysis will be performed for this purpose. And based on this, we determine what Ryugu is and how attractive the sample is. Having introduced that to the world, we want to share the sample and analyze. The curation facility will be created on these premises. This is to be built from now. With regard to Hayabusa2, it's completed. And this is called a chamber. And it's important, Mr. Tachibana said, that we determine it's actually a sample from the Ryugu. We have to make sure that things do not mix from the earth, and so we seal it. And before it comes into this the atmosphere, we introduce it into this facility and take out the contents of the container. And this has just been completed this year, and it's a picture taken from above. What's bad about samples coming into contact with the atmosphere or the air? Water and organic matter is a key word in scientific analysis. When you say water, we have vapor in the air, and when you say organic matter, human beings are organic matters, and so we don't want to contaminate the sample. So we will handle the sample in this facility so that it does not come into contact with the air. So is it a vacuum? There's a part of it which is a vacuum, and then a nitrogen, pure nitrogen. The first half is just vacuum, and the back half is nitrogen. And specifically, what kind of analysis will you perform? The analysis we perform in the project is one which we will be doing with the researchers of the world. We have created 6 teams. Ryugu sample, scientific, chemical features, isotopes, and elements will be checked. And then what will be collected are rocks. And rocks have different minerals. It's a mixture. And so the rocks and compounds will be checked by 2 teams, one dealing with the larger particle, the others with the smaller particles. And the volatile matter, there are items prone to become gases. We hope it'll be there. And this is related to the ocean and life. And there are people who will be analyzing that. And there's another team looking into organic matter. And there are 6 teams altogether which will be engaged in the analysis. All will be performed in this chamber. Within the chamber, we will check the nature of the substance, and photographs will be taken, and catalogs will be made. The actual analysis We'll be using state-of-the-art devices. Without coming into contact, the samples will be placed in boxes, and it will be analyzed in Japan and in other parts of the world. So without coming into contact, the samples will be contained in a box, and it will be distributed. And that's the process we call curation. And in Japanese, it would be selection. Selection of rocks, senko. Curation is a word which we want to popularize. In museums, you have curators. So these very valuable items collected from different places should be categorized and stored and managed, and if necessary, presented to the researchers. All of this is referred to as curation. So these are the two curators. Itokawa particle distribution is something I was involved in, and I am involved in that even today, every day. Hayabusa1 sample distribution is being done in the adjoining room, and on the other hand, we're making preparations for Hayabusa2. So the two rooms are separated. And Itokawa was mentioned. In the case of Itokawa, the sample volume was smaller than expected. How much was the volume? I don't remember.
When you opened it up, there was nothing that was seen. That was how little the volume was. And then some particles that are even smaller than the tip of the hair strand. And there were about 700 of them that were picked up. And they were distributed to the different countries in the world, and the research is still ongoing. And with Hayabusa2, the samples are coming back and brought back. So how much do you expect to see? Well, the nominal 100 milligrams, so a spoonful of samples. In the case of Hayabusa1, you are not able to see anything at a glance, but you're expecting to see a spoonful. Well, touchdown was successful today. We're not sure if the projectile was actually fired, but if it was, then something that is visible at least will be brought back. We expect that to happen. And then ejector. It's not the projectile that we're talking about this time. That SCI, the impactor. Are you talking about the impactor? Yes. The impactor, more samples are expected to be collected, right? Well, the sample collection is done by the sampler horn that is on the screen. And the impactor is there to create crater in the asteroid to extract the substance inside under the ground of the asteroid. And with the solar wind, the substance may have been changed on the surface. And how many centimeters? If you dig how many centimeters, some centimeters deep, then you would be able to pick up the rocks that had not been affected by the solar wind. And so that's what the impactor was doing, designed to do. So the impactor is not there to actually scoop a large amount of samples. So it's almost like being sunburned on the humans. There is a lot of particles flying in with the solar wind, and that's what we call space weathering. And particles that are not affected by that should be collected with the from the crater where the SCI has worked. So after the sample return, if you become busy, then that will be the best. Yes. So all the members are now called to join the joint photo. So thank you very much. So you're looking at the control room now on the screen, and all the project members are gathered to take a commemorative photo. And so all the members are now moved to the control room with all smiles. And they are now in the control room for the group photo.
はいはいはい。 しばらく管制室の様子をご覧いただいておりました。
We showed you how things were developing in the control room. We're drawing near to time to close. Back to the studio. We want to extend the program a little bit. We will be broadcasting until about 20 past 9. The last guest we have with us is the director of JAXA, Dr. Kuninaka. The JAXA ISIS director, Dr. Kuninaka. Hayabusa2 and asteroid exploration. Beyond that, could you discuss some broad themes? Back to the image, please. This is. We'd like to first of all thank you for supporting the Hayabusa2, and let me talk about what lies ahead. What you're looking at is the solar system. The closest to the solar system is Mercury and Venus and Moon, the Mercury and Jupiter and Saturn and so forth. A lot of explorers are within the solar system. The first explorer that we launched was what we launched called the Halley Comet, Sakigake, and the two explorers. 1985 is when we successfully launched it, and since then it's been, well, including plans for the future, over 20 explorers, the spacecraft, have now been launched into the solar system, and some of them are Japanese explorers, and then there are those which we have developed jointly with the United States and Europe, belonging to us. Last year, in October, as a joint program with ESA, Bepi Colombo is the explorer we launched toward Mercury. 2018 was the launch in October, and it'll land in 2025. It will land on Mars. It's an ESA-JAXA joint program. Japan created MIO, the explorer, and Europe's MPO. Two explorers will jointly explore Mercury. And what is under development is SLIM to land on the moon, and we are in the development process. It's a 100-meter scale, high accuracy, pinpoint landing technology, which we wish to acquire through this. It's the major target. 2021 is the time we plan to launch. Close to the equator of the moon, Mickey's Ocean is where it is expected to land. Mantle substances where rocks are exposed. We want to land the spacecraft, and we wish to conduct precise analysis, an accurate analysis. And further in the future, we have MMX, Martian Moon Exploration Program. bringing back samples from moons of the Mars. There's Phobos and Deimos. These are moons, Martian moons. We want to land on either of these moons to collect samples to bring that back to the Earth. It's a large-scale project. 2024 is the scheduled launch, and 2025 is when it was expected to land at the destination, and it will observe Phobos Deimos, and it will land on either, and it will collect the sample and come back to Earth. 2029 is the scheduled time for return, and that is also a major project. 2025 it'll start its activities on the Mars atmosphere, and the Osaka Expo will start at this time, and we want to present real-time photographs from the Mercury at Osaka Expo, and also with regard to asteroid Phaeton flyby project. Destiny Plus is a mission which we went, and the launch is scheduled for 2020. And the asteroid Phaeton is the mother planet of the Gemini, and by precisely observing this is believed to be the origin asteroid that brings a lot of comets to the Earth. And JUICE and JAXA joint product. Several observation devices have been contributed by ourselves, will be provided by ourselves. And Jupiter Ganymede is where we want to spread our observation. 2022 is the scheduled timing of launch, and at the Jupiter moon Ganymede, on the surface there's ice. Underneath the ice, there's an inner ocean, the inner ocean on this planet, and we want to do an observation of this. And the sample return of the kind, the sample return from Hayabusa will be returned to Earth in 2020 in a capsule. We want to develop the sample return technology further. Hayabusa 1 and 2, the capsules that will be used will be a larger size, which will be sent on MMX. This will be used for sample return from Mars. And a larger capsule is under development at the moment. This is a joint program with NASA in the United States. And Caesar is the name of the mission. Terimus Brascomus will be where the Explorer will be sent, and samples will be returned, and it will be brought back on a large sample container. It's a large project. And the key words here is water. There's a lot of water, people think, on Earth, but if you could see on this chart, on Earth, compared to the volume of the Earth, there's only 0.1% of water around Jupiter and around Saturn. Europe, Callisto, Titan, and Ganymede, these are the moons. The size of the body is very small compared to the Earth, but the water contained is a vast amount. And that is what people think. And what this means is that inside the solar system, from Mercury to Saturn, there are rock planets. But beyond that, there is Jupiter and Neptune and Pluto, which are gaseous. And there's a lot of water there in the form of ice. And after the creation of the solar system, beyond the smaller line, water was brought back from Jupiter and Saturn, people think. And it would be comets and asteroids and cosmic dust. These small celestial bodies contained water, and that was brought to the Earth, according to some. And the important role was played by movement of substances within the solar system, and it's cosmic dust and asteroids and comets which played a major role. And we're trying to do more research into this missing piece through our work. And as is shown here, we distributed a lot of explorers into the solar system. We want to gather data from multiple number of explorers, and through the swarming system, 4.6 billion years of the solar system will be explored. And that is what the ISIS wants to do. And this is the exploration strategy. It involves not only the solar system, but with regard to space, PRISM X-ray imaging spectroscopy is being developed. In 2016, there was an accident. We lost STRO-H. This is the successor unit to that. In 2021 is the slated or the development target date for launch. CRISM, this is X-ray spectrometry, and infrared telescopic speaker, a microwave telescope, LightBird is what we're contemplating, X-rays, infrared, and radio waves. We want to integrate all of these here, to try to clarify the 3.6 billion years of history from what has started with the Big Bang. We want to bring all of these frequencies together to try to explore the history, which started with the Big Bang. And as mentioned, ISIS's astronomical and solar system research is, as I have explained. We hope that you will continue to support and cooperate with us in our endeavors. In particular, to the younger people, please do take on the challenge of doing work in space and technology and JAXA and other space-related projects. We hope that you would participate so that you could join with us in trying to develop our future. And that is the message from me.
So there was a failure of Hayabusa 1, but all of those lessons were learned and corrected in Hayabusa 2. But that is reflected in all the explorations and the research and opening up the frontier of space. The technologies and science that are required to do that will be accumulated going forward. So as the head of the ISIS, he has covered all the areas and has given consideration to all the areas. But at the outset of the program, well, you may have heard this, but there was some commitment shown by the head of the ISIS, but that was prior to the launch. Well, at the time of prior to the launch, you shouldn't uncover our secrets, but actually at the Tanegashima island, right before the launch of the rocket, the words that he shared with us, similar to those were given, and I was moved back then, but I'm quite impressed that this has been web streamed on the internet, so everybody got to hear what he had to say. So I was very pleased. So Imamura-san was one of those members that were inspired. And there's one comment from the Twitter, Bartman, JAXA and ISIS, all the ISIS members. The success and achievements are not the result of the research activities, but this can give the power and dream and hope to the children. And I really pay utmost respect and congratulations to all of you. Well, that was the message, and I think this room is also filled with passion, and those viewers that are watching this program through the web streaming, we are hoping that this passionate atmosphere can be conveyed to the viewers watching this program. Mr. Hosoya has come back from the control room, so can you give us the update? So I'm back. Well, currently at the control room, the Gate 5 completion was declared, meaning that the Explorer spacecraft is on its way back to home position. And so Gate 5 has been successfully passed. And there's not going to be any major development in the control room anymore. So with the completion of Gate 5, the program is complete. So stay tuned for the press conference that will be held from 11 o'clock this morning. And there will be program manager present, and there will be an official announcement. And the press conference will also be live streamed. So thank you very much. And I would like to thank all the viewers for their encouraging words.